All right, this is the first QQT question from Unit 1. A dart with a mass of m sub d is launched towards a block of mass m sub b, suspended from a string of length L. After the collision between the dart and the block, the system then swings up to a point at which its center of mass reaches a maximum height h above its starting position. The block's mass mb is greater than the dart's mass. So I guess we might as well write that. If you want a better drawing, it's on your quiz there. So A, indicate which object, the dart or the block, if either, experiences an impulse of larger magnitude during the collision. If it's the same, state it explicitly, briefly explain your reasoning. So impulse, remember, is F times delta T, and it's equal to the change in momentum. So as we know, the dart on block and block on dart force are equal and opposite. It's an action-reaction pair. And the time they react on each other is the same. So the impulse are equal. So both experience the same impulse. So there were a couple of ways you could reason this. You could explicitly say the forces are equal, the times are equal. Impulse is the product of those, and so they have the same impulse. You could also say it's an action-reaction pair, so that they experience the same impulse. You could also get that point for explaining it in terms of the change in momentum, although that seems kind of like an odd way of doing that. So 1 point for indicating that they both have the same impulse or they both experience the same impulse, and for an explanation thereof. Part B says, if the speed of the dart as it embeds itself into the block is greater than v, how would the maximum height reached by the center mass of the dart block system compare to h? Explain your response without deriving or manipulating equations. So remember that we're still talking qualitatively at this point, okay? So the answer is it would go higher, which I think is probably pretty obvious, but let's talk about how. I would use conservation of energy here. So you get for this 1 point for indicating that the final height would be higher, and a point for indicating that the final velocity of the block plus dart is higher. And so by conservation of energy, it would go higher. Let me say that a little bit better. First, we have by conservation of momentum, right? The mass of the dart plus block is going to be higher in case 2 than it was in case 1, right? Because we have mass of the dart, velocity of the dart equals mass of the dart plus mass of the block times our final velocity here. So we could reason that if the velocity of the dart were higher in this case 2, then this would be higher. And then we'd have to say, we use conservation of energy and say 1/2 mv squared equals 1/2 mgh. So the higher velocity resulting from that collision would lead us to a larger h there. So that's the reasoning there. By conservation of momentum, we know that this final velocity will be higher, and then by conservation of energy, we know that this will be higher. So 1 point for the conservation of momentum conversation, and 1 point for the conservation of energy, for a total of 2. Okay, so now for the statements by the students where we need to figure out which one is correct and which one isn't. So, or both. 2 students are discussing the motion of the dart block system the instant it reaches h. The students make the following statement. Student 1 says the speed of the system at height h is 0. Since it's moving in circular motion and centripetal acceleration is given by a as v squared over r, then acceleration must be 0. Okay, so what was correct? For C, the first statement was correct by that student. The speed of the system at height h is 0, okay? However, and this is part D, the incorrect statement by this student is that the acceleration is also 0. We know that the net acceleration, keeping it in a circle, is v squared over r, but that is a combination of tension and the gravitational force. on there. So the second statement by that student is wrong. Okay, the acceleration of that block is not 0. All right, now E and F ask the same questions for student 2. Student 2 says the acceleration at the height h can't be 0, or the system would not swing back down. The acceleration must be equal to g at height h. Okay, so the correct thing that student 2 said was the first statement. Okay, the acceleration of the system at height h can't be 0. If it were, and there were no forces acting on that block, it would just stay there. So that reasoning was correct. The incorrect reasoning or statement was the second one. It says the acceleration must be equal to g at height h. But remember that at height h, it's not in free fall. There's tension in that string. So that's how those work. Now, you'll notice it doesn't say to justify your answer here. So you're allowed to just write those and move on to the next part of the problem. So now we switch over to the quantitative part of this problem. And it says, the students correctly derive an equation for the maximum height, h equals 1 over 2g, mass of the dart times the velocity, divided by the sum of the masses, and we square that. Okay, so they've used that from the mgh equals half mv squared. Explain how this equation supports your claim in part B. So hopefully your claim in part B was if the speed of the dart were higher, the height would be higher. So here's how we justify this. H is directly proportional to V. It's actually proportional to V squared, but that doesn't even matter right now. If the velocity increases, the height is going to increase. So what you need to do is what they call state this functional dependence, okay? V is in the numerator of that fraction. If V increases, then H increases. So you get 1 point for indicating this functional dependence. As you can see, the height is proportional to the square of the initial velocity. And then 1 point for indicating that by this function, if V increases, the height increases. So 2 points for part G. And part H says, which quantities could you graph to produce a straight line whose slope can be used to find acceleration due to gravity g? Now, don't confuse this with what could you graph so that the slope is equal to g. They don't need you to do that. They just need you to produce a straight line so that we can use that straight line to find the slope. So what we need to do is plot h versus v squared. Okay, if I want to write this again, I get h equals 1 over 2g. I'm going to put my v squared over here, and I'm going to get at the mass of the dart, plus the mass of the bullet squared here. I can take that v squared out. So then what you would do it, and we don't even have to do this. They're just asking what could you do. Graph h versus v squared, and then this is your slope. 1 over 2g, and then you've got the masses ostensibly, and you could just solve that algebra problem to find h. Ideally, I would say plot v squared on the x-axis and h on the y-axis. You could make an argument for plotting something else with h on the other axis. I would not plot h versus v because you're not going to get a straight line, okay? So you can't use that to find the slope. So once you decide what you're going to plot, something versus v squared, the rubric is weird. The rubric says 1 point to plot v or v squared on one axis, and then another point for plotting something with h on the other axis. Oh, I see what they're saying. You could either plot h versus v squared, or you could plot v versus the square root of h. Yeah, I guess I didn't see that the first time. So 1 point for dealing something v on this axis, and then 1 point for the appropriate thing on the y-axis. So like you would not want to quote v squared or plot v squared versus rad h, that's not going to work. It's got to be h versus v squared or rad h versus v for those 2 points. And then 1 point for saying that if you did that, this would be a straight line. Okay, this would be a straight line. So 3 points for part H. And now in a classic twist, they say for part I, after the collision, the dart block system is then allowed to swing freely, and the students produce the graph shown at left, labeled group 1, of the vertical position of the center of mass of the dart block system as a function of time. A second group of students makes a second single change to the setup and then repeats the experiment. Their graph labeled group 2 of the vertical position is shown. So I says indicate the single difference in either dart mass, initial dart speed, block mass, or string length between the setups that could lead to the difference between the two graphs. So what you need to realize there is that once it starts to oscillate, we have a pendulum. And the only thing that affects the period of a pendulum is the length of that pendulum. I suppose I should have said, by looking at the graph, you should realize that that group 1 has a longer period than group 2, right? Group 1 has a longer period. Group 2 has a shorter period. So you needed to realize that. Then you need to realize that the only thing that affects the period is not the mass of the bob, not how fast it's going, but the length of that pendulum. So what happened in group 2 is that they shortened the string. That's the only thing they could have done to get that result. So for part I, 1 point for realizing that the period got shorter, 1 point for realizing the dependence of the period on the length, and 1 point for saying that the shorter period means it must be a shorter length in group 2. So that's it for that first QQT.